We have mentioned this fact several times before, but let's mention it again, and that'll help us see how the rank-nullity theorem comes into being. So let's let A be any m by n matrix. Remember, the image space, it's all of the right-hand side vectors B and Rm, where m is the number of rows, such that this linear system, Ax equals B, is consistent. So it's all of these things that make this linear system consistent. And then remember, the column space of A, that's just the span of all of the column vectors in the matrix A. So the theorem here says that the column space is actually equal to the image space. Here's an example illustrating exactly why we should expect the image space of a matrix to be equal to the column space of a matrix. So remember, the image space, so let's let A be this 2 by 3 matrix, so A, B, C, D, E, F. And check the columns are A, D, B, E, and C, F. So what are things that are going to live in the image space? So the image space, remember, that's going to be contained in R2, so the number of rows. So now, a 2 vector UV lives in the image space if and only if this linear system is consistent, right? So this matrix A times some vector in R3, call it XYZ, is equal to UV. So again, UV is in the image space if and only if this matrix equation is consistent. So you can just now multiply this matrix by this matrix, and then you get this thing, right? AX plus BY plus CZ. So AX plus BY plus CZ, and then DX plus EY plus FZ. Now that has to be equal to the vector UV. So now, when is it true that this vector is equal to this vector? Now we're going to take this thing and split it up along x, y, and z. So that's AX dx, right? AX dx, and then factor out an x and you just get AD. So x times AD, and then plus y times BE, and then plus z times CF. So now this thing has to be equal to UV. So now we can see that UV is in the image space if and only if UV is a linear combination of the columns of A. In other words, UV now lives in the column space of A. So that's if and only if. Chase it backwards. If UV is in the column space, that means it's a linear combination of the columns. And then you can take these columns and add them up, right? Scalar multiply and then add them up and you get this thing. And then this is the same thing as take the matrix and multiply by the column vector x, y, and z. So this is why the image space is equal to the column space. And we know a lot about the column space already. Alright, so here's the 4 by 5 matrix A that we've been looking at. So we computed the null space of this thing. We saw it had dimension 2, and then we computed the image space. We saw it had dimension 3, and that's good because 2 plus 3 adds up to the total number of columns, which is 5. So how do we find the image space? Well, we augmented with some vector with components A, B, C, and D, and then put that thing in row echelon form. We got a constraint equation, and then using the constraint equation, we found these 3 vectors. So here's an easier way to find the image space. It's really just the column space. So if we can find the column space, then that means we will have found the image space, only it's a much easier process to compute the column space. So instead of augmenting with A, B, C, and D, all you need to do is just take this thing, put it in reduced row echelon form without the A, B, C, D, and then pick out the pivot columns, so 1, 2, and 4. So columns 1, 2, and 4, that's going to give us, so that's going to give us the column space. So here we want 0, 1, 2, -1. So we've got 1, 2, 3, 4, so column 1, and then 2, 5, 7, 9, that's column 2. And then column 4, that's the last pivot column, we get 0, 1, 2, negative 1. So these two things are supposed to be equal, even though they look different. So we've got the image space is the span of these three vectors in R4. We've got the column space is the span of these three vectors in R4. And we claim that these two things are equal. Is it possible that you can have three different spanning vectors and give you the same spanning set? So for example, we know that the span of 1, 0 and 0, 1, if you just look at all the reachable points in R2, right, everywhere you can get to using these things, that's all of R2. But we can use other spanning sets to reach all of R2. So for example, we know that the span of, let's say, 1, 1 and 1, negative 1, right? These two vectors are linearly independent, and there's two of them, so you can get to anywhere in R2, right, using these two directions. So these two things are equal, even though they've got different spanning vectors. So like this one, call it x, y. These two vectors, call them z and w. So you've got the span of x and y is equal to the span of z and w, even though the pairs of vectors are not the same. So that's what's going to go on here. The span of these three vectors is the same as the span of these three vectors. And we know that the theorem says that these two things have to be equal, right? These two things have to be equal. Therefore, these two things must be equal. So maybe we can show that really quick. Why are these two spanning sets equal? Just to see that these two sets of vectors span the same space, I'm going to take each one of these three vectors and arrange them as rows in a matrix, right? So column 1 is row 1, column 2 is row 2, column 3 is row 3. And then do the same thing with this list of spanning vectors. So what is the span of these vectors as it relates to this matrix? Well, the span of these vectors is the same as the span of these rows, which is the row space. How do you find the row space? Put the thing in reduced row echelon form and then pick out the non-zero rows. This thing is already in reduced row echelon form, so the row space of this matrix is exactly, well, I don't need to write it again. The row space of this matrix is exactly this thing. It's the span of these three vectors. Do the same thing here. Take these columns and arrange them as rows in a matrix. Put this matrix in reduced row echelon form. The non-zero rows make a basis for the row space. So these non-zero rows, these non-zero vectors make a basis for the row space. That means these three vectors make a basis for this spanning set. These are the rows, right? So these two spanning sets both have the same row space. They both have the same basis, right? They've got this common basis that you can find using the row space. So that means this spanning set, because it's got the same row space, must be equal to this spanning set. So that'll do it. Here's the rank-nullity theorem. And so remember, the rank is the number of non-zero rows of the matrix when you throw it in the RREF form. So another way to write rank, that's the dimension of the column space. Remember, it's just the rank is the same thing as the number of non-zero rows. It's the same thing as the number of pivot columns, right? So that's the dimension of the column space, and we saw that these two things are equal, so the rank is also the dimension of the image space, and the rank is the image of the row space. So all of these things are the same thing as rank. So the number of pivot columns, that's the rank. And we know the number of columns is the number of pivot columns plus the number of free columns. The number of free columns is the dimension of the null space. That's the nullity. So this is essentially why you get the rank nullity theorem. So that's definitely something you want to commit to memory. The number of columns is equal to the rank of A plus the dimension of the null space.